Welcome back to the Explainer. We type prompts into these large language models every single day, and human-like text just magically appears on the screen. But actually, it's not magic at all. It's this incredibly fascinating, highly structured sequence of math and logic. Let's lift the hood and see exactly what's going on in there, step by step.
To shatter the illusion right out of the gate, I want you to think about this classic problem. Why did hyper-advanced AI struggle for so long to just count the R's in a simple word like strawberry? Well, it's because we naturally assume the AI is reading letters exactly like we do, but it isn't. An LLM absolutely cannot see letters. It doesn't even see words. It literally only reads numbers. And that brings us to the first massive transformation in our journey.
Before the model even glances at your text, your prompt goes through tokenization. It basically chops your words up into these sub-word pieces and assigns each one a token ID. So the word running might get split into run and ning. Strawberry gets sliced into arbitrary chunks that have absolutely nothing to do with the individual letters. Because the model only works with these integer chunks, well, asking it to count letters is kind of like asking someone to describe the intricate brushstrokes of a painting when you're only letting them look at the price tag. It's doing math with integers, not reading the alphabet.
Okay, so here's our roadmap. We're going to follow the exact chronological assembly line of a single text prompt. First, words into numbers. Second, order and attention. Third, the deep processing layers. Fourth, predicting the next word. And finally, number 5, the future of AI architecture.
All right, step 1. Words into numbers. This is all about giving real meaning to the math.
So we know a prompt gets turned into arbitrary integers, right? But an integer like, say, 1024 is literally just a number. It has zero inherent meaning on its own. So how on earth does the model actually give it meaning? It does it through scale. Just immense, mind-boggling scale. Take a look at this number, 4096. In a standard 7 billion parameter class model, a single token isn't just one tiny integer. The absolute second it enters the model, it gets expanded into a massive vector, a list of 4096 numbers.
Now, where does that massive vector even come from? It comes from something called an embedding matrix. Just think of it as a giant lookup table. Your token ID goes in, and this deeply complex, perfectly learned vector of 4096 numbers comes out. And here's the really wild part. Semantically similar tokens naturally end up grouped closely together in this giant matrix. By training on just mountains of text, the model learns completely on its own that the vector for king should physically sit closer in space to queen, and Paris should be right next to France.
And because meaning is now physically mapped to this geometric space, you can actually do arithmetic with concepts. This famous equation perfectly proves the point. If you take the vector for king, you subtract the vector for man, and then add the vector for woman, the resulting numbers land almost exactly on the vector for queen. It's incredible. Nobody hard-coded this geometry. It just magically emerged from the model, reading billions of pages of text.
Moving right along to step 2, order and attention, connecting the context.
Okay, so now we have these embedding vectors absolutely packed with deep semantic meaning. But there's a pretty glaring problem. That vector alone has literally no idea where it sits in a sentence. The vector for dog is the exact same whether it's the very first word of your prompt or the 50th. And obviously, word order completely changes meaning. So, to fix this, we need positional encoding. The original 2017 method, additive positional encoding, basically took a fixed sine wave pattern and just jammed it directly into the token's numbers. But that crowded the vector and really didn't scale well for super long prompts. So the modern solution, the one used by models like Llama and Mistral, is rotary position embeddings, or ROPE. Instead of adding new numbers, ROPE mathematically rotates the vectors by an angle based on their exact position. So a token at position 1 gets a tiny little turn, while a token at position 100 gets a massive turn. It is just a beautiful way to solve the problem of tracking relative distance.
So, now the tokens know what they mean and exactly where they are. Next, they need to talk to each other. Enter the famous attention mechanism. Every single token suddenly takes on 3 roles at once, kind of acting like a detective. It generates a query, asking, hey, what am I looking for? It generates a key, saying, what do I match with? And it generates a value, what gets copied when a match actually happens. Using a scaled dot product, the model scores how perfectly one token's query lines up with another token's key. So if your word is sleeping, its query sweeps across the sentence looking for a subject, and boom, the key for the word cat lights up, linking those two together across the text. But language is way too complex for just one single attention pass. We need multi-head attention so we can track grammar, pronouns, and repeating phrases all at the exact same time. In the early days, models used full multi-head attention where every single query head kept its own keys and values stored in memory. We call that the KV cache. The issue, that eats up a massive amount of memory for long prompts. So modern models shifted over to grouped query attention. Here, multiple query heads actually share fewer key and value heads. It is a brilliant trick that saves absolutely crucial memory while still keeping that amazing parallel processing power intact.
Step 3. The deep processing layers. This is where the knowledge actually lives.
All right, we're leaving the collaborative world of attention now. We're diving into the hidden, kind of unglamorous machinery where individual tokens do their own heavy lifting, totally independent from one another. This all goes down in the feed-forward network through a very strict 1-2-3 sequence. First, expand the token's vector to an even larger size. Second, apply a nonlinear function. This nonlinear bend is absolutely crucial. Without it, stacking all these layers of math would just collapse into one totally useless flat layer. And finally, compress the vector back down to its original size.
Now, you might be wondering, why do we even do this? Well, the feed-forward network is essentially the model's hard drive. It's where the model stores all its real-world facts. Stuff like the Eiffel Tower being in Paris. But trying to pack all those facts in makes the model enormous. Enter this brilliant trick called mixture of experts, or MOE. Instead of one giant feed-forward network, the model has several parallel networks. These are the experts, and a router sends each token only to the specific experts it actually needs. To really put into perspective how effective this is, take a look at the model Mixtral 8x7b. It boasts a completely staggering 46.7 billion parameters in total. But because of that MoE routing, for any single token going through, the model only actively uses 12.9 billion parameters. It's a total game changer. It lets us build these absolutely huge models with massive amounts of memory without the computational costs just completely skyrocketing.
But here's the catch. If you stack dozens or even hundreds of these layers together, the math gets wildly unstable. So how do we stop the training signal from just exploding or completely dying out? The secret sauce is residual connections. Instead of completely replacing a token's vector at every single step, we just add the new output back to the original vector. It creates this sort of shortcut stream right through the entire network. Coupled with a neat stabilizing trick called RMS norm, this keeps the numbers totally in check. It's literally the vital trick that lets us stack hundreds of layers safely.
Step 4. Predicting the next word. The output loop.
Okay, we've made it through the tokenization, the embeddings, the attention, and the deep layers. Let's hit the final stage of our assembly line. How does all this ridiculously dense math finally spit out a human-readable word? Well, we take the final vector of the very last token in our prompt, and we convert it into raw scores for every single possible word in the entire vocabulary. We call these raw scores logits. So right before the model guesses the next word, that one final vector has blossomed into tens of thousands of raw numbers. Finally, we pass those numbers through a function called softmax, and that turns them into clean percentages, the actual probabilities of what should come next.
But the model doesn't always just pick the number one highest probability word. Honestly, that would sound incredibly robotic. Instead, we get to control this giant statistical slot machine using settings like temperature. If you've ever asked an AI to write highly strict factual code versus, say, a wildly creative poem, you've totally seen this in action. Turn the temperature down low, and the model becomes super conservative and precise. Turn it up high, and the distribution flattens out, letting the model pick slightly less common words, generating really varied, creative text. Oh, and to speed this entire loop up, modern systems use something called speculative decoding. That's where a tiny, super-fast model guesses a few words ahead, and the big model just double-checks the math. It speeds up the output dramatically before the whole process loops back around to start again.
Step 5. The future of AI architecture. Let's see what comes next. So we've spent all this time in the micromechanics. Let's zoom out to the macro landscape and look at what this all means for AI development. If you look closely across the landscape at models like Llama, Gemini, or Claude, what you'll find is this shocking convergence. They almost all share this exact same skeletal structure: the tokens, the embeddings, the attention heads, the residual streams. It's practically universal at this point. What actually differs isn't really the underlying architecture. It's the trained weights, the sheer scale of their configurations, and exactly how heavily they are instruction-tuned after their initial training. Which naturally leads us to a massive question.
For the first time in history, one single architecture, the transformer, is absorbing everything. It's doing text, it's doing vision, it's doing audio. So we really have to ask, is this architecture the final master key to artificial intelligence? Or, with new alternatives like Mamba, state space models looming on the horizon promising massive context lengths, is this whole thing just a brilliant stepping stone to whatever comes next? I'll let you ponder that. Thank you so much for joining me on this explainer. Keep learning, stay curious, and I'll catch you on the next one.